this. Um, let's start with the question number 1 on the pre-class quiz of last week. Okay, do you see my screen?
Yes, we can, sir.
Okay, great. So these questions ask about the question is about the representations of relations. On the left, we have graph representation of two relations, R and S. Both relations are defined on the set A, containing 4 elements A, B, C, and D. And you are asked to determine or to choose which of the matrices on the right is a representation of the relation S circle R, the composition of S and R. Yeah. Okay. What is our first step to solve this?
To find the matrix representation for both R and S, sir.
Okay, that could work as well. So what would be the matrix representation of R and S?
For R, it is 1110.
Okay, 1,
Yeah.
1, and then 1 and 0, assuming that this represents element A, B, C, and D, right?
Yes, sir.
And then for B, you have 1, 1, and then 1 and 0, right?
Yes, sir.
Okay, good. And for C, you have, what about C?
1100.
1, 1, 0, 0, and for D?
0001, sir.
Okay. All right. And for S?
1100.
1, 1, 0, 0, correct.
And then 1100 again.
And for B, yes, 1, 1, 0, 0. And then for C, it's 1,
1011.
1, 0, 1. 1. Yeah. And for D, you have 0, 0, 0, 1. And then what would you do?
And then in this case, because it is a circle R, I multiply the matrix R with matrix S, sir. R times S.
Okay, R times S. So you all right, R times S. Yeah. Why is not S times R? Well,
Because the relation R is connected first and then followed with S.
yes. So you have R first and then S. Yeah. So in that case, we simply multiply them. The multiplication is done over I think this is pairwise multiplication, isn't it? Element-wise multiplication, right?
Yes, sir. Normal matrix multiplication.
Right. So that means, so let's put it. This is the matrix for M. So the matrix for S circle R is matrix of R S, and this gives us what? What will be the result? One,
1 1 1 1, sir.
1 1 1. Hold on a second. Why 1?
In
Actually,
this
it's
case, I think it should be there. There is a coefficient. I forgot the coefficient, but then we take like the boolean. If it's not 0, then we consider it as 1, sir.
All right. Let's check the definition, right? So the definition says that the uh, matrix of the composition of the relation, then it is actually a Boolean product, right? Yeah, a Boolean product of of the uh, of the matrix. So it's common matrix multiplication, but you perform Boolean multiplication instead of the usual number or integer multiplication. So in this case, what we do is let me. Where is my eraser? I missed it. All right, so let's start from the first element, right? So what we do is we look at the first row and the first column of RNS. So here 1110 times 1110, and the multiplication is a Boolean multiplication. That means it's a 1, right? And then for the second element, you multiply 1110 with 1100. So in this case, it's so it's 1 times 1 or 1 times 1 or 1 times 0 or 0 times 0. The multiplication is defined as an operation in this case, right? So therefore, this is a 1. Yeah. And similarly, you do the same thing. This is also a 1 because 1110 multiplied with 0010. So you at least have the C here. So 1 times 1 here, right? And then for the last column, 1110 times 0011. So you have the third element, 1 here and 1 here. So you still have 1. Yeah, good. Now the next row is 1110 times 1110. So it's a 1. 1110 times 1100. It's a 1 as well. And then similarly, this is also a 1. And this is also a 1. Yeah. And then for the third row, so 1100 times 1110 gives us a 1. Remember, because you have 1 times 1 plus 1 times 1 plus 0 times 1 plus 0 times 0, where the plus and the times or multiplication is defined as or an an AND operation, right? Good. So what about this one? Has to be
1,
why is
sir.
it 1? Good. Now how about this one? It is a 0, right?
Yes, sir. 0.
Yeah, it's a 0, and also for this one. And finally, here you have a 0 here. You have a 0. You have a 0, and you have a 1. Right? Is this your solution?
It is, sir.
Yes. Great. So that would be which one? I think should be this one, the first one, right? Yeah. Good. Or is there any one of you who did it by creating the graph first? Does anyone solve this by creating the graph for
Sir,
the,
excuse me, sir.
yes,
I think you circled the wrong answer, sir.
did I?
Yes, sir, I believe so.
Oh, yeah, you're right. I think I did circle the wrong answer. Yeah, so sorry about that. So it has to be, should have been the third one, right? Should have been this one, right?
Yes, sir, I believe so.
Yeah, good. Does anyone solve this by constructing the graph first before creating the matrix? Here, the step is we construct the matrix and then we multiply the matrix. But is there anyone who solve this by constructing the graph first and then getting the matrix out of it? No one? What do you think? Is it more difficult or is it easier? Which one is easier? Constructing the matrix first and then multiply them like this, or constructing the graph first and then get the matrix out of it? What do you guys think? Which one is easier?
I prefer creating the matrix first, sir.
Okay. Any other opinions? Does everyone agree?
When I tried using the graphing method, sir, there were too many lines to draw, and it made me lose track of what I was doing.
Okay, good observation. Yes, indeed. Yeah, yes, indeed. If you construct the graph first, then you may find it difficult because you have so many lines. You may lose track of those lines. So, for example, in this case, you if you construct the graph first, then you might want to start with A, and then from A, where can you go, right? Using two hops, using R and then following it by S, right? So it's kind of complicated, right? All right. Um, good. Now, number two. For number two, okay, which of the following is the reflexive closure of R and S? So what would you do? You would get R and S first, right? What is this?
A, C, sir. Alone.
A comma C. Anything else? Just this?
If I'm not mistaken, yes, sir.
Yeah, it is. It is. It is the only element of R intersection intersected with S. So then the reflexive closure of this is what? A comma C and then
A comma A, sir.
A comma A
B comma
and then
B,
US.
C comma C.
Correct. So you simply add the main diagonal elements, right? If you represent this as a matrix. Reflexive closure, right? Now, therefore, the answer is where is it? Second one, right? No, not the second one. I made mistakes again. Should have been the fourth one. Yeah. Good. All right. Any questions? So, no question? Not then just making sure here. Reflexive closure is the relation you obtain by ensuring the original relation to be becomes reflexive by adding more elements that allows them to satisfy the properties, right? So, in this case, the reflexive closure to get the reflexive closure of R intersected with S, what you do is you add A comma A, B comma B, C comma C. Yeah. Yeah, at least, so you have to add those three elements in order to make it reflexive. Good. Now, how about the next one? Which of the following is the symmetric closure of R? What is the symmetric closure of R then? Which one? First, second, third, or fourth? Is the first?
It's not the first one, sir.
Okay, not the first. Why? Well, you could simply compute it, right? So symmetric closure of R is R itself C comma C, C comma A, N, C comma C, and then you add further element to make it reflect, to make it symmetric, right? So in this case, you add B comma A, C comma A is there already, so you add C comma B, right? So therefore, the answer is
The third
B,
one, I
One,
guess.
sir.
the third one. Yes, correct. Yeah, good. Why not B comma A and C comma? Why not this? Why not this one?
Because it's the set union with the original one to get the reflexive closure, sir.
All right, so it's the union of this set with the original relation R to get the symmetric closure of R. Right, that is correct. So B comma A, C comma B are the two elements that you add to the relation to get a symmetric closure, but that's those two elements by themselves do not form the symmetric closure of R. Good. Now, question number 4. Which of the following relations should be combined to S? Remember, should be combined to S such that the transitive closure of S is obtained. So if you have S is this element, yeah, B comma A, C comma B, yeah. What you add is first what do you add to make it transitive?
AB, sir. A comma B.
A comma B, because you have AC and CB, right? So you add A comma B, right? So or let me write it down. Uh, um, no, it's fine. This is true. Yeah. So let me just label this with R1. So that means S union R1 is A comma C, B comma A, uh, C comma B, and then A comma B. Right. What else? R2. What do you add more?
B comma C, sir.
B comma C. So it's A comma C, B comma A, C comma B, A comma B, B comma C. Because well, from A to B, you have sorry, from A to C, C to B, you get A comma B, and then from B to A to C, you get B comma C, correct? And then what do you add more?
B comma B, sir.
B comma B. All right. Yeah. So that means becomes, first let me just write it down. A comma B, uh, A comma C, B comma A, B comma B, B comma C, and C comma B. Yeah. And then you add more, right? 4. What do you add? A, B, B, A. You add A, right? So S union R1 union R4 becomes A comma A, A comma B, A comma C, B comma A, B comma B, B comma C, and C comma B. All right. Next, what do you add more? Well, you add
C comma A, sir.
C comma A. Yeah, because you have C to B and B to A, right? So therefore you add C comma A. So you have S union R1 union R5 is A comma B, A comma C, B comma A, B comma B, and C, B comma C, and then C comma A and C comma B. What else? Well, finally you add actually C comma C, right? Because that's the only, and you have to add C comma C because you have C comma A and A comma C, right? So that means S union R1 union up to R6 is actually the whole Cartesian product, right? Yeah. So the transitive closure of S is actually, let me call the set here set A. It's the Cartesian product of A and A. Yeah. So the answer is for this question is actually R1 union up to R6, which is A comma B, B comma C, A comma A, B comma B, and then C comma A and C comma C. Yeah. So that is A B. So A B, B B, B C, C A, and C C. So this is the answer, right? Any question? Is it clear?
Yes, from me, sir.
All right, good. Question number 5. Question number 5, the question is to determine the small set containing R and has the reflexive, symmetric, and transitive property. So it is essentially asking about equivalence closure, because equivalence relation is a relation that is reflexive, symmetric, and transitive simultaneously, and therefore the smaller set containing R that then has those and satisfies those 3 properties are equivalence relations, so it's equivalence closure. Yeah. Now, so what? How do you answer this question? First of all, yes.
By checking each option, actually, sir.
Yes, but what do you check first?
The reflexive property and then followed with the remaining, sir.
Good. Okay. Yeah, that is one. Yeah, I think the easiest one to check is reflexivity, right? So clearly, 2, 2, 3, 3, and 4, 4, 1, 1, 2, 2, 3, 3, and 4. All of them are reflexive, right? Yeah. This is also reflexive. What's next?
Symmetric, I believe, sir.
Checking symmetry. Okay. Let's check whether they are all symmetry or do we have not symmetry. So the first one is symmetric, right? What about the second one? Is it symmetric? Yes, right? How about the third one? It is also symmetric. And the last one, is it symmetric?
It's not, sir.
Not symmetric. So we cross this out. So yes, we cross this out. Now we only need to check 3 options. What's next? What do you check next?
Transitivity, sir.
You check transitivity, or do you check whether the set, whether the relation contains R?
That could work.
Yeah.
Actually, yes, sir.
Yeah, actually that's easier, right? So let's check, right? So is R contains 1, 2, 1, 4, 3, 3, and 4, 1, 1, 2, 1, 4, 3, 3, and 4, 1. So this contains R. What about this one? 1, 2, 1, 4, 3, 3, and 4, 1. It does also contains R. Also contains R. So all of them are all of them contain R. So now all 3 of them, right? So now what then it remains to check the transitivity. So let's check the transitivity. Which one is not transitive? Well, the third one is definitely transitive, right? Because it contains all possible pairs involving the set 1, 2, 3, 4, right? So the third one is transitive. What about the first or the second? Let's check the second one. Is it transitive or not?
It's not, sir.
Why?
We have 2, 1, 1, 4, but not 2, 4, sir.
Correct. So not transitive. Not transitive. So we cross this out. There is my pen. Here it is. So what about the first one? Yeah, I think
It
this
is
is
transitive, sir. It is transitive.
Yes. So what is our answer?
The first one, sir.
The first one, because it's the smallest. Yeah, the smaller one. Yeah, good. Question number 6. Which of the following is not an equivalence relation on A? So how do we solve this? Equivalence means it has to be reflexive, has to be symmetric, and it has to be transitive.
The same way we solved the previous question, sir.
Correct. So what we do is we simply check. So this is reflexive. This is reflexive. This is also reflexive. This is also reflexive. What about symmetry? This one is also symmetry. This one is also symmetric. Is it? Yes, right. 1, 3, 3, 1, 2, 3, 3. Yes, symmetric. And this one is also symmetric. And this one is 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. So it is symmetric. So now what remains is to check the transitivity. Let's go with the third one, which is the smallest. Is it transitive, this one?
Yes, sir, it is.
Transitive. Okay, this is transitive. What about the last one?
It is also transitive, sir.
Yeah, because this covers the Cartesian product of A times A, right? Now, what about the first one? It is transitive, right? Yeah. And the second one is definitely not transitive because what?
We have 2, 3, 3, 1, but not 2, 1, sir.
Correct. So not transitive. Yeah. Yeah. So one, for example, 1, 3 and 3, 2 is in the relation, but 1, 2 is not in the relation. Yeah. So this is not an equivalence relation. Good. Q7. Which of the following is not an equivalence relation on the set of integers? Okay, pardon the Indonesian language here, but yeah. So which one is not an equivalence relation? So let me check. Let's call it R1, R2, R3, and R4. All right. So R1, is it reflexive?
Yes, sir, it is.
It is reflexive. Yeah, because x plus x is 2x, which is even. So that means x comma x is in R1. Yeah. And is it symmetric or not? Well, yes, right. Symmetric, right? Why? If x comma y,
Because
yes. What is it?
addition is commutative, sir.
Yes, then x plus y is even. Then of course y plus x is also even. Thus, of course, y comma x must be in the relation R1. Good. Is it transitive?
It is, sir.
Yes, transitive. What is the argument?
If we take like x plus y is even and y plus z is even, then x plus z is also even, sir.
Correct. So x plus y and y plus z are even. So x plus y plus y plus z are even. Yeah, or is even. Yeah. So sorry. Yeah, this is even, which is so x plus z is of course x plus y plus z minus 2y, and which is even. Yeah, good. So this is equivalence relation. How about R2? So R2. R2 is reflexive, right? Because x, since x is less than or equal to x. Yeah. Is it symmetric?
No, it's not, sir.
Not symmetric. Why?
We can provide a counterexample. For instance, 4 is less than or equal to 5, but we cannot say that 5 is less than or equal to 4.
Correct. Yes. Yeah. So not symmetric. So then you actually get the answer, right? Which is this one. Yeah. It's easy. Now, of course, the question may be show that, for example, R4 is an equivalence relation. Yeah. So the way you do it is similar to this. Yeah. Yeah. Right. Good. Any question? Yeah. Because you already get that R2 is not symmetric, then this is definitely not an equivalence relation. Yeah. Good. How about you? You said 8. Now, which one is a representation of an equivalence relation?
The last matrix, sir.
The last matrix. Okay. Okay. Rather than going straightforward with the last matrix, I want to ask, why are the first 3 options not an equivalence relation? What about this one? This one is easier, right? This is not an equivalence relation because of what? This one.
It's not transitive, sir.
Not transitive, correct. Which one? Which arrow is missing?
A to C, C to A, B to D, D to B, sir.
Correct. So because, yeah, A to B and B to C is in the relation, but A to C is not in the relation. Yeah, good. What about this one?
Also not transitive, sir.
Good. Yeah, not transitive because,
C to A to D, but now C to D, sir.
yes, correct. Yeah, so C to A and A to D is in the relation, but of course C to D is not in the relation. Good. Yeah. So what about the first one? The first one is easy, right? This is not reflexive.
Reflexive.
Yeah, good. So yes, the answer is this one. Yeah, it is reflexive, it is symmetric. And well, to check transitivity, how do you check transitivity of a matrix representation here?
Graph it, sir.
Yeah, you make it a graph, or you perform uh, 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 so a relation R is transitive if and only if this holds, right? Right? So what you do is you multiply the matrix. Yeah. So let's check. So let's multiply this with itself, right? So you have 1 0 1 0, and you have 1 0 1 0 1 0 1, and then you have 1 0 1 0, and then 0 1 0 1. You multiply this Boolean multiplication with itself, and then 0 1 0 1, and then 1 0 1 0, and 0 1 0 1. What will be the result? The result is, well, this one is 1, yeah, and this is 0, this is 1, and this is 0, But this one, 0, 1, and then 0, and then 1, and then 0. So this is 1, 1 0 1 0 times 0 1 0 1 is 0. This is 1, this is 0, and then of course 0 0 1. Yeah, and this is actually the matrix of R, right? So yeah, so in this case, it is um, um, uh, uh, so this holds, right? Yeah. This represents R, right? Yeah. Good. Now, what about this one? Okay. Now, what will be a good answer to this question?
The first one, sir.
The first one. Why?
Because by the concept of partition, when we union the partition, it should reform A. But then in this case, the string ending with 1 0 is not covered, which means we cannot reform back the original set, sir.
Yes, good. Yeah, yeah. So the union of the sets do not form A. Yeah. Essentially, we are missing those bit strings ending with 1 0. Correct. Yeah. Good. So this is not a partition. Yeah. The rest is a partition. Yeah. This is a partition. This is also a 1 1 1 0 1 1 1 0 1 0 0 1 and bit strings ending with 0. So ending with 0 and ending with 1, but then you have 0 1. You have both of them, 0 0 1 1 0 1 and 0 1 1 and 1 1. Yes. So this is a partition. And but the last one, even number of ones and then this odd number of ones. Yes, this is also partition. Good. Let's have a look at this one. What about this one? How many equivalence classes?
3, sir.
3. Okay, how do you get 3? What are they? What are the partitions? What is the partition? The member of the partition. So you have 1,
1, 3, and 4, sir.
3 and 4, and then
2 and 5.
2 together with 5, yes, and then
6.
6 by itself, yeah. So with that, I think it is easy, right? So this one, it should be this, and this, 2 and 5, and then 1, 3 and 4, 2 and 5, and then, oh, sorry, here, a mistake here. Yeah. So it has to be 1, 3 and 4, and then this one is 2 and 5, and 6 by itself. Yeah, good. Yeah, to solve this, actually, you just simply take one element and then well, assuming that the if the relation is already equivalent, an equivalence relation, then you take all elements reachable from that element, then you collect them together to get one part of the partition. Yeah. What question number 11? All right. What is the cardinality of R? So
14, sir.
14. So what how do you get this? Well, first, yes. What do you do?
We reconstruct the tuples from the given partition, sir.
Yeah, good. Yeah, so we take 1, 1. What about from the second partition?
2,3 and 3,2, sir.
2,2, 2,3, 3,2, and 3,3, right? Now from the last one, well, 4,4, 4,5, 4,6, and then of course 5,4, 5,5, and 5,6, and 6,4, 6, 5, and 6,6. Yeah, good. Yeah. Yeah, so that would be the tuples, and therefore we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So the answer here is 14, and you simply check all the tuples, right? So 1, 1, and then 2, 2, 2, 3, 3, 2, 3, 3, and then of course 4, 4, 4, 5, 4, 6, 5, 4, 5, 5, 5, 6, and then 6, 4, 6, 5, 6, 6. Yeah, good. This one is easy, right? Question 12. Now this one. Set A is a set of prime numbers less than 30, and the relation R is the relation of x comma y such that 5 divides x minus y. And this is an equivalence relation, right? Because it's actually the same as saying that x is equivalent to y modulo 5, right? So what is the cardinality of R? So how do you solve this? Well, set A consists of 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, right? And therefore, so the so R is set of x comma y in A times A such that actually x is congruent to y modulo 5. Yeah, it's the same as this, right? So therefore, here R contains what? 2 is with
7, sir.
7,
And
or yeah, and I think it's easier
and
to
itself.
yeah, I think it's easier to write down the partition, right? So let me write the partition. Yeah. So let me write the partition. So the first partition contains 2 together with 7 together with what else? 17,
17.
and that's it, right? Yeah. What about the other partition? 3 together with
13.
13, and then
23, sir.
yes, and then you have another partition 5
And itself, sir.
by itself, 7 already there, not 7, then 11, right? 11 together with
Itself also.
by itself, and then 13 is there already, 17 is there already, 19
With 29, sir.
with 29. Good. Yes. So these are the partition. Now from here, you get how many tuples? So from the partition to 7, you get how many tuples?
I
4.
think the partition is 2, 7, 17, right, sir?
Oh yeah, sorry about that. Sorry. Yes, indeed. Why did I add this? Yeah. Um, so it has to be so let me just erase this first. So so from here, from the partition 2, 7, 17, we get which pairs? So we get this pair, right? This pairs here. So 2, 2, 2, 7, 2, 17, and then 7, 2, 7, 7, 7, 17, and then 17, 2, 17, 7, and of course 17 and 17. So here, this is 9 tuples. From the partition of 3, 13, and 23, you get 9 tuples, right? From the partition of 5, you get 1 tuple. Partition containing just 11, you also get 1 tuple. And then partition this, you get how many?
4 tuples, sir.
4 tuples, right? So total 9 plus 9 plus 1 plus 1 plus 4, 24 tuples. Yeah. So the continuity of R is 24. How many partitions are formed? We got it already. How many? It's a 4, right? Now choose all member of the equivalence class of 2. So it's 2, 7, and 17. What about 11? 11 is 11 by itself. What about 19? 19 is 19 and 29. Yeah.
Sir, I believe there should be 5 partitions. I think you missed the 2, 7, 17 one.
Oh, yeah, correct. So it should be 5 partitions. Yeah. Yes. Good. Any questions so far? No? All right. So if not, so let's move on to pre-class quiz for this week. Yeah. Or maybe let's take a break for 5 minutes. All right. Let's take a break for 5 minutes and we'll go back. Let me resume the recording. Yes. So let's start with the pre-class quiz for today. So but before that, let me just recap the notions regarding the partial order. Right. First, a partial order is over a set is a binary relation on that set that is simultaneously reflexive, antisymmetric, and transitive, right? So partial order is relation that is reflexive, antisymmetric, and transitive. Yeah, good. Uh, well, I should say non-strict. So do we have a strict partial order? Yes, we do, right? So strict partial order. So relation that is, what is the difference between non-strict and strict partial order?
It is irreflexive and asymmetric, sir.
Irreflexive. Well, uh, you could also say antisymmetric and transitive, right? Well, note of course irreflexivity and antisymmetry together imply asymmetry. What happened with my, yes, yeah, so it is also possible to say it that way. Yeah, good. Now we have strict and non-strict partial order. So therefore, in this case, the answer is for this one. Why is it not a strict partial? Why is it a not, sorry, not a non-strict partial order? Not a non-strict partial order does not mean that it is a strict partial order, right? So it could also be not a partial order at all. Yeah. So in this case, let's have a look at the properties of R. R is not reflexive. Yeah. Not reflexive. Is it antisymmetric? It is, yeah. And it is actually, well, not transitive, right? So therefore, here the answer is R does not have the following properties, namely reflexivity and transitivity. Yeah, good. Any question? No? Okay, no. I take it as a no, all right? So what about Q2? Oops. Q2? Q2 does not satisfy what?
Anti-symmetry, sir.
Antisymmetry. Which one? Which pairs fails this test?
1, 1, 3, and 3, 1, sir.
1, 3, and 3, 1. So 1, 3, and 3, 1 is in R, but well, 1, 1, and 3, 3 are not in R. Sorry, not this one. This is not what I meant. This is wrong. Oops. Yeah, here the answer is what? 1 is not equal to 3. Yeah, There are different elements. Now, what else? Is it reflexive? It is, yeah. Is it transitive?
It's not, sir.
It's not, yeah. Not transitive, yeah. Why? Because you have, well, you have 1, 3. Sorry, not 1, 3. Let's have another.
4, 1, and 1, 3, sir.
Oh yeah, 4, 1 and 1, 3 is an R, but 4, 3 is not an R. Yes. Good. Yeah. So is it reflexive? It is reflexive, right? So we saw that already. Now, how about this one? Here, the answer is R does not have the following properties. Well, does not have reflexivity. Oh, a strict partial order, right? Sorry. Something is wrong. So it's not a strict partial order, right? So strict partial order has to satisfy the reflexivity and then anti-symmetry. These together gives us a symmetry, and then also of course transitivity. Now therefore here you see that this does not satisfy irreflexivity. What else? Does it satisfy anti-symmetry?
It doesn't, sir.
It doesn't, yeah, it doesn't satisfy anti-symmetry. Because this, and of course it fails asymmetry, right? Because you have 1, 4 and 4, 1 in R. Yeah, 1 is not equal to 4. Yeah. Yes. Yeah. Okay. Good. Next, question 4 is not a strict partial order. Yeah, so a strict partial order because of what? It does not have which property? It doesn't satisfy. It doesn't satisfy anti-symmetry, right? Or in this case, asymmetry. Yeah, because you have 2, 3, and 3, 2 there. Yeah, 2, 3, and 3, 2 is in R. Yeah. And also, it does not satisfy transitivity because here we have that 1, 4, 4, 3 is in R, but 1, 3 is not in R. Yeah, good. What's next? Q5. This one. Okay, is R reflexive?
Yes, sir.
Yes. 1, 1, 2, 2, 3, 3, and 4, 4. Is R antisymmetric? Antisymmetric should it be?
Yes, sir.
Yes, yeah. Yes, okay, good. Is R transitive? Answer is?
Yes,
Is
it
it a
is.
yes? Yeah, it is yes. Yeah, so 1, 2, 2, 4. You have 1, 4. Yeah. Oh, the easier way to to do this is by drawing a graph, right? Drawing a poset, but with the arrows. So essentially, you start from 1, so you could go from 1 to 2. Yeah, well, 1 to 2, uh, and then from 2 to 3, and 3 to 4. And but you also have 1 to 3, you have 1 to 4, then you also have 2, 4, and so on. Yeah. So you could draw it that way as well. But let's go on with the next question. So are element 1 and 2 comparable?
Yes, sir. We have
Yes.
1, 2, and 2,
Yes.
1.
Yes. And then yes, it's a yes, and it's a yes. So R is a total order or not a total order?
It's a total order, sir.
It's a total order. Good. Now, so what is the difference between a partial order that is not a total order and partial order that is a total order? What's the difference?
One of the elements in a partial order that is not a total order is not comparable, sir.
Okay, good. Yes, very good. So let's have a look at this one. This is a Hasse diagram for the poset S comma R. So the set, the underlying set is S and the relation is R. And R is a partial order. Now, if X is equal to G, which elements satisfy the value Y? So essentially, yeah. So G comma Y is in R when Y is equal to what? Yeah. What would be your answer?
G, comma G, G, comma D, G, comma E, G, comma F, sir.
Correct. Yes. Very good. G, B, E, and F. Yeah. Nice. So, and then I think we have a question number 7. Here's a Hasse diagram. Okay. So now we want to determine the minimal elements and maximal, smallest, and greatest elements. All right, and also lower bound, upper bound, and whether the poset is actually a lattice. So let's recap, right? So minimal elements, X is minimal if what?
No other element in the set precedes X, sir.
Yes, or that is if there is no Y such that uh, Y comma X is in R. Yeah, X is maximal if there is no Y in the set such that X comma Y is in R. In the set A. So assume that this is underlying set is A. Yeah, and then of course smallest if
It's unique, sir. The minimal element is unique.
yeah, or what would be the definition without referring to the definition of minimal elements? So when is X smallest in A? If
If it precedes all other elements in the set, sir.
yeah, so that is if X comma Y is in R for every Y in A. Yeah. And then X is greatest or largest, greatest is probably the better way. In A, if, well, if it is larger than every other, right? So that is if Y comma X is in R for every Y is in A. Yeah. Now, let's determine the minimal elements. What will be a minimal elements of the poset?
A, B, and C, I believe, sir.
A,
A and
A
B, I
is
mean. A and B, I mean.
A and B. C is not, yeah, because C has another element smaller than it, right? What about the maximal elements?
E and F, sir.
Correct. So the E and F, yes, E and F. Smallest element of the poset
Doesn't
We don't
exist,
have
sir.
one, sir.
doesn't have one. What about the greatest element of the poset?
Also none, sir.
Also none. Okay. Now the next question is about upper bound and lower bound. So lower bound of set B, which is a subset of A, is
A
is
set,
what?
a set of elements that precedes all elements in the B, sir.
Correct. Yes. So if is a lower bound, just a lower bound is an element Y in A such that Y, so or to say the relation RY comma X. Sorry, Y comma X is in R for all X in B. Yeah. Similarly, an upper bound of set B, so A is an element Y of A such that X comma Y is in R for all X in B. So it precedes, a lower bound of a set is an element that precedes all elements in that set, and an upper bound of a set is an element that, what was it, follows, yeah, what do we do, precedes, succeeds the all elements in that set. So in this case, a lower bound, a lower bound of CD would be what?
A, B, and C, sir.
Correct. So A, B, and C. Yeah. And then an upper bound of CD.
D, E, and F, sir.
Yes, D, E, and F. Yeah, good. What will be greatest lower bound? So greatest lower bound is a lower bound. Yeah, well, obvious, right? It's a lower bound that precedes all other, that succeeds all other lower bounds. And a least upper bound is an upper bound that precedes all other upper bounds. Yeah. So therefore, the greatest lower bound of CD is
C, sir.
C. Yes, greatest least upper bound of CD is D.
D.
Yeah, very good. Now, the next part is the poset a lattice or not?
It's not, sir.
Why?
Because the set A and B has no greatest lower bound, and the set E, F has no least upper bound, sir.
Yeah, so a lattice is a relation, yeah, is a poset. Poset is a poset is a lattice if every pair of poset, say S comma R, is a lattice if every pair X comma Y in S Sorry. So you have to check every pair. Every pair of elements x and y in S uh, if yeah, it has a GLB and uh, this upper bound. Yeah. So if we check this, well, we check, well, obviously CD so has a GLB and this upper bound. But for example, AB, yeah, AB has a least upper bound, but not greatest lower bound, right? Because it does, because we don't have an element that precedes A and B, all of them, yeah, that precedes A and B. So it doesn't have a lower bound in this case actually. Yeah? So it's not a poset. So it's not a lattice, I should say. Right. So let me ask a question. What would be, or let's just so let's just do this, right? So if I have this as a lattice, is it so I have this poset, right? Is it a lattice or not?
It's not, I think, sir,
Why?
because B and D. Oh no, never mind, never mind.
BND has a greatest lower bound.
Yes, it's a lattice, sir.
Good, it is a lattice. How about this one? Yeah. What about this one? Is this a lattice or not? Should be easier, right? This is not a lattice because
B and D has no lowest upper bounds.
BND has a least upper bound,
Uh,
right? A or sorry, B itself is a least upper bound, right? BND. The answer is because E and F has no uh, has no uh, least upper bound. B and D has a least upper bound, namely D. Yeah. Okay. Good. Any question? Any question about poset and lattice?
None from me, sir.
No. Okay. Um, So let me ask a question. Is a transitive closure of a symmetric closure of a reflexive closure of a relation an equivalence relation?
It is, sir.
It is. How do you prove it?
Well, by the definition of a closure,
Mhm.
for instance, we start from the first one. A reflexive closure of a relation uh, must be reflexive in the first place. And
Correct.
then a symmetric closure of it then must also be symmetric, and as it contains the reflexive property,
Mhm.
it then must be both symmetric and reflexive, sir. And
Okay.
then it follows the same argument for the last transitive closure, sir.
Yes. So essentially, when you form the closure, then you don't lose the other properties, right? So that's the main idea, right? Yeah. Now, how about this? Uh, is a symmetric closure of a of the reflexive closure of a of the transitive closure of a relation, an equivalence relation.
It should be, sir.
Okay. Is it a yes or no?
It is an equivalence relation.
Really? Does everyone agree? Does everyone agree? Okay. So let's check. All right. So let's check. Let's define a relation R, which contains 1, 2, and then 2, 3, and then 1, 4. All right. On set on the set A 1, 2, 3, 4. So the question is the symmetric closure of the reflexive closure of the transitive closure of a relation an equivalence relation? Here, the transitive closure of R is what? Let's call it R2. Should be what? Should be 1, 2, 2, 3, 1, 4, and 1, 3, right? Is that it? Yeah. Is this the transitive closure of R?
Yes, sir, it is.
Yes. It is transitive and it covers R, right? So now the reflexive closure of R2 then, right? So what would the let's call it R3, reflexive closure of R2 in this case is of course then 1 1 1 2 1 3 1 4, and then of course 2 2 2 3, and then 3 3 and 4 uh, 4 4, right? And 4 4. Yeah. Okay. So this is obviously transitive. What about this one? Is it reflexive? Obviously, yeah. It is reflexive. Is it transitive? Anyone? Is it transitive?
Yes, sir, it is.
It is transitive. Good. Now, let's form the symmetric closure of this. Let's call it R4. The symmetric closure of R4. Yeah. Then you have actually 1 1, 1 2, 1 3, 1 4, and of course you have 2 1, 2 2, 2 3, and you have 3 1, 3 2, 3 3. Yeah. And you have also 4 1, uh, 4 1, and then what else? From the one above, and 4 4, right? Yeah. Is that the correct symmetric closure of R3? Yeah, you add 2 1, you add 3 1, you add 4 1, and you add 3 2. So you have 2 1, 3 1, 3 2, and 4 1. Yeah, good. This is a symmetric closure of R3, right?
Yes,
So
sir.
it is reflexive. Is it symmetric? Yes, obviously. Now my question is it transitive or not?
It's not, sir.
It's not transitive, but not transitive. So here the answer here is no, not necessarily. Yeah. So be careful there, right? Yeah. So why is it so? Can you give me a fundamental reason why?
I think it's because the transitivity closure was provided first, sir. So by actually providing a new set of tuples while creating the symmetric closure, some of them might actually be not transitive in that stage, sir.
Yes. So that is actually true. Yeah. So this transitivity relies on the characteristic in that if you have two pairs connected in such a way, then you get a third pair, right? Now then, when you perform the symmetric closure, you add more pairs. So you add more pairs, and this then you have to make sure also that the added pairs do not violate the transitivity. So therefore, in this case, it's not necessarily transitive because we found here, in fact, that adding more pairs introduce violation to the transitivity. Good. Yeah. Um, what else? So let's see. Do we have a question on partial ordering? Let's have a look. Um, So give a pose set. So let's do this, right? Let's have one example. So give a pose set that has a minimal element but not a maximal element. Give a pose set. Anyone can give me a suggestion here?
Less than or equal to over positive integers.
Less than or equal to over positive integers. You mean this one? Less than or equal to 2?
X is less than or equal to Y.
Oh, okay. Okay, good. Yes, it is indeed. Yeah, it has no maximal element. The minimal element is
1, sir.
it's 1. No maximal element. Why?
Because the number of positive integers are infinite.
Okay, yeah, maximal element. Well, more formally, because if y is a maximal element, yeah, of the plus comma r, then uh, so let's call it z. Yeah, z is a maximal element of. No, let's call it b. If b is a maximal element of this poset, then b is such that then x is less than or equal to b for every. No, sorry, not this one. Should have been what will be your reasoning then? B, then there is no c in positive integers such that b is less than or equal to c, right? Is it this is right, the reasoning, huh? Yeah, but b plus 1 is in z plus as well, and also b is actually less than or equal to b plus 1. Yeah. So b cannot be maximal. Yeah. So, but give me an example of, is it possible to have a finite poset that has a minimal element but not a maximal element? Is it possible to have it that way? Can we have a finite poset? Can we have a finite poset
If the set is fine, if the relation is the same and we change the domain of the set into like a finite set, sir.
Okay. Oh, hold on a second. You're saying that something like this R on, let's call it R2. That's correct. Like this,
Yes, sir.
where A is like something like this.
It's a finite set. Yes.
Really? So minimal element of R, A R2 is 1, right? But it has a maximal element, right? Its maximal element of AR2 is 4. What do you think? Does R2 have a maximal element? I think it has.
Yes, sir, it does. It have.
So R2 here is not a R set, right? It has a maximal element. Eh? Right? Is 4 a maximal element of this set?
It is, sir.
Yeah, it is. So this is not our example. What about? So, but still the question is, can we have a finite set, meaning that a set on where the underlying set is finite, the underlying set is finite, such that it has a minimal element but not a maximal element. Or in other words, if A comma R is a poset that has a minimal element but no maximal element, then can A be finite? So what do you think? What do you guys think? Is it a yes or no?
What if the domain is like a range of real numbers between, let's say, 1 and 4, sir, but inclusive in 1 but exclusive in 4, sir?
But that set is not finite, right? You're saying that this set, a real number, such that something like this? Is that what you're saying?
Yes, yes, it's not finite. It's not finite.
It's not finite. Okay. What do you think? So does A have, or is A necessarily finite, necessarily infinite in this case? Is it possible for A to be finite? That's the question. If we know that here, that the poset has a minimal element but no maximal element. Okay. Well, I think it is impossible for A to be finite. What do you think? I think it is impossible for A to be finite. What do you guys think? So is my remark correct? So it is impossible for A to be finite. That is, A must be infinite. What do you guys think? Is it true that A is impossible to be finite?
I think it's true, sir, because whenever we actually have the, say, the upper bound of the interval, that
Mhm.
upper bound will always be the maximal element, because it, in that case, it will not precede uh, any other element of the set.
Mhm.
So I believe it must be infinite, sir.
So so because you're saying that because uh okay so repeat that again. So you're saying that because
Because there is always the greatest element in the interval.
what do you mean
That
the interval? What do you mean the interval?
well, if we say like uh or say finite set, for instance, sir.
Okay.
Yeah,
So
for
let's call
instance,
it,
there.
yeah, let's call it
Yeah,
the finite set, right? So let's write it down. Yeah. Suppose A is finite. So what do you mean? Then what can we say about A here? Then what?
then there is always an element that doesn't precede any other element, sir.
So supposing that A must be like something like this, right? A1, A2, and so on up to AN, all right?
Yes, sir.
And then what? You're
as
saying
as there is that element that does not precede any other element in the
element,
set.
element, say, set call it AJ, yeah,
Yes, sir.
yeah, such
That
that
AJ does not precede
does not precede
any other element in the set A.
any other element in the set A, yeah? Or in other words, what
AJ
does
is
it?
the maximal element
Hold on a second. Why? Why do you? Why are you sure? We don't know we don't know R here. How can you? How can you be sure that there is such an element? How can you be sure that? How do we know that there must be an element that does not precede any other element? So we cannot assert that way uh, without providing a more explicit argument. We note that, of course, A here has n elements. N can be anything, right? N can be a lot of those elements. How do we know that there must be such a J?
Yes, sir. We actually cannot do that, sir.
Yeah. Okay. I think it
Because at
is.
least,
Yeah. I
yeah,
know where you're going with that. You're saying that if you have a finite set, then that finite set must have a maximal element. That's what you're saying, right?
yes, sir. Initially, yes.
Yeah. But we have to show that it is actually the case. So we have to show that if A is finite, then and A does not have a maximal element with respect to R, then something breaks. Yeah. So that's what we have to show, right? Um, so something like uh, let me erase this. So something like yeah, something like this. Uh, suppose also A has no maximal element. Yeah, that is every element in A is not a maximal element, right? Yeah, every AI in A is not a maximal element with respect to R. Yeah, that is, what does it mean? It means for every AI in A, there is always another element that uh, 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 um, so AI always precedes at least one other element, right? That's the idea, right? There is an element AJ not equal to AI, of course, such that um, hold on a second. For every AI in A, there is an element AJ Okay. I think we got an idea here, right? So, um, let me erase this. There has to be an element AJ um, in A such that AI comma AJ is in R, right? Yeah, there is always such an element. Yeah, otherwise Otherwise, AI will be a would be a maximum element, right? So because AI is not a maximum element, that is always this. Yeah. But the key here is that there is only a finite number of AJ, right? So say uh, uh, um, but if this is so, so then let's first assume that AJ is not equal to AI. All right. Then we can construct, of course, right? We can construct a chain of pairs of the form something like uh, uh, something like AI, AI1, AI2, and then AI2, AI3, and so on, yeah, up to AI n, AI n plus 1, right? Yeah, such that all of them are in R, and all AI1, AI2 up to AIN is in A. AIN plus 1 is in A. Are in A. Yeah. Now here, notice that not that, of course, AI1 is not equal to AI2. And then AI2 is not equal to AI3. Yeah. And also AI1 cannot be equal to AI3, yeah, because otherwise AI otherwise R becomes symmetric, right? Which is not our, right? So, and thus all of AI1 up to AI n plus 1 are should be different elements. But we only have n elements in A, right? Right? Yeah. So because we only have n elements in A, then at least two elements amongst AI1 up to AIN plus 1 are equal. Yeah. If they are equal, then R becomes symmetric. Yeah, yeah, which contradicts the fact that R is a partial order. Now, so our assumption is wrong, but which assumption is wrong? So the assumption, the latest assumption, this one is wrong. The assumption that AI is not equal to AJ is false. Hence, if A is finite and AR is set with a minimal element, but no maximal element, yeah, then R must be what? Must be the set here. A1, A1, A2, A2, up to AN, AN. Yeah. So the only way but let me make sure that my answer is correct. Is this a partial order? Is this set a partial order?
It is, sir.
It is a partial order, right? So yeah, so in that case, the only way to have to make sure that A comma R is a poset with a minimal element, but no maximum element. Okay, but hold on a second here. Does it have a minimal element? A minimal element must be, it does have a minimal element, right?
It has both, yes, sir.
Yeah, it has a maximal element as well, right? So, okay, so our assumption is wrong, yeah? That in that case, where is my eraser? So, actually, you're right. So then R must be this, right? Why is it not working? So if A is finite, then R must be this. Yeah. But of course, also we note that but also that this R has a minimal and maximal element. So that means A must be or cannot be finite. So that's essentially our proof. Yeah. All right. So A cannot be finite in this case. Yeah. All right, any question? So yes, so we have an example, a post set of with minimal element but no maximal element, and in this case the underlying set is infinite. But we can show also that in general that if a post set has no maximal element, then that post set, the underlying set, cannot be finite. All right, good. Yeah, any question?
None from me, sir.
No? Anybody else?
None from me as well, sir.
Okay, good. If there's no other questions, I think we can end the sessions early. And we finish all the content on the post sets as well. And we will have a break next week because of the Eid holiday. And we will meet again after the Eid holiday. And we will discuss graph by then. All right, I'll see you guys 2 weeks from now.
Okay, sir. Thank you, sir.
Okay, thank you, sir.
Thank you, sir.